Section 3.3 is going to have us diving a little bit deeper into the graphing of quadratic functions. Now, I know when we very first started talking about quadratics in the last section, we were looking at representations, and we did start, I guess it was 3.1, we did look at the table of values, and we looked at the graph it generated, just for the most basic of all of our parabolas, y equals x squared. In this section, we're going to take a look at more complicated quadratics and how to graph those. So, keep in mind, a quadratic function always can be written in the standard form, which would look like f of x equals ax squared plus bx plus c. And really the defining feature, the reason that we know this function is quadratic, is that the highest power of x is 2. Right? That's how we know it's quadratic. Now, we're not always going to be given our quadratic functions in standard form. And what we'll see in this section is that, in fact, sometimes some of the other forms are actually even more useful or useful for specific reasons. So we know that there's 3 forms of a quadratic function, right? There's the standard form, there's the vertex form, and then there's the factored form for at least some of them. We'll look at all 3 of those forms and see what each one tells us best about what our graph looks like. All right, so just real quickly, rather than having to redo this, I'll remind you, we generated this table and this graph back in section 3.1. And we had mentioned then that one of the most important points on the graph is the turning point, which could be a local minimum, like this one, or we'll see in a little bit that that parabola can actually turn upside down, in which case we might have a local maximum. But either way, it'll have one turning point, and that turning point is called the vertex. The vertex is one of the most important points on the parabola to make sure you have in the right place when you graph it. In this particular parabola, the vertex is 0, 0. It's right at the origin. If I were to draw a vertical line through the vertex, which in this case is right here on the y-axis, that forms sort of a mirror line for our parabola, right? The parabola is almost like looking in a mirror. It's perfectly symmetric on each side of that axis of symmetry that I just drew. In this particular case, the axis of symmetry is actually the y-axis. Or if you remember, vertical line, all the x values are the same. So the equation in this case could be x equals 0. X is 0 along that entire line. All right, as we graph more parabolas, we'll make sure we always locate the vertex and the axis of symmetry. And then the other thing that's going to be important is the x and y intercepts. So the vertex, axis of symmetry, and then x and y intercepts are going to be the things that I'm going to try and make sure we have right in order to draw a reasonably good sketch of any parabola. All right, one other thing to notice here, just sort of in general before we get down to some specifics, is that unlike a line, right, a straight line, which either increases or decreases all the time, a parabola does both, right? If you look up at this graph again, the parabola decreases for a while, and then after the vertex here, it increases. So if we're describing a parabola, rather than just say it increases or decreases, we're going to give the interval for which it increases, and then the interval for which it decreases. So in this particular graph, this parabola is decreasing until we get to the vertex. Now, when we describe the interval of decrease, we actually give the x values that are associated with that part of the graph. Those x values would go from negative infinity to 0. right? All of those x values are associated with a decreasing graph. So I'm describing the x values, not the y values. So I'm going to say here, and I actually did the second one first, the interval of decrease goes from negative infinity to 0. All right, after we hit x equals 0, our parabola is going to increase for the rest of the way, right? It goes uphill now, or increases. And the increasing part of that parabola is associated with x values that start at 0 and then go on forever to positive infinity. So our interval of increase, we listed as the x values from 0 to infinity. And the thing here that's just sometimes a little bit hard to get used to, but once you're there, you'll be fine, is that we're always looking for x values when we talk about intervals of increase and decrease. All right, we'll label those intervals for some more parabolas here as we go along. All right, the first set of quadratic functions that I'd like to investigate graphing are actually not going to be the ones in standard form. I'd like to start with ones that are in vertex form. So if you remember, the vertex form of a quadratic function looks like that, right? We still see the x is going to be squared, so the highest power still would be 2, but it's just given in a slightly different form than the standard form. When that happens, the values of a, h, and k actually make the parabola change in a very predictable way. We call this the transformation of the graph of the parent function, f of x equals x squared. So essentially what we're saying is this is kind of always our starting point. That parent function, x squared, and we already know how that graph looks, right? It looks like this. We'll start with that, and then we'll make transformations or changes to that graph based on the values of a, h, and k to predict what the new graph is going to look like. All right, in order to investigate this, I'm going to look at what happens with some of these changes by just graphing a few examples in Desmos. And notice the first change I want to look at is what happens if instead of f of x equals x squared, I put a negative in front of that. F of x equals minus x squared. So I'm just going to graph y equals x squared first, our standard parabola. And then I'm going to do y equals minus x squared. And what you can see is it's literally turned it upside down. In kind of math speak, we usually say it's been reflected across the x-axis, right? It is its own mirror image across the mirror line of the x-axis. So when I describe what's happening here, that's what I'm going to say. The graph looked like this. And as compared to the parent function, the original function, which was this, our new graph is reflected across the x-axis. That's the very mathematical way to describe it. In your head, you can kind of think upside down, right? Sometimes we say the parabola opens down. You'll hear all of that from different people at different times. All right. Next thing I want to investigate is what happens if we have a multiplier in front of our x squared. What I'm going to do, since I already know that the negative is going to reflect it, turn it upside down, I'm only going to investigate positive multipliers here because we could predict what happens with those And then if it was a negative multiplier, we know it would just flip upside down. So let's take a look at some multipliers. Let's see. I've got that y equals x squared already in there. Let me put in 2x squared, 3x squared, oops, squared, there we go, and 4x squared. Did you see what happened to the graph? It appears to be getting sort of narrower in a way. What's actually happening here is we have what we call a vertical stretch. So you might notice, for example, here, when the y value was 2 and the original parent function, 2x squared, it was stretched all the way up here so the y value was 4. And so on and so forth, right? 3x squared, it was stretched all the way up so that the y value was 6 for that same point. So we call this a vertical stretch, and essentially the graph is kind of getting almost like taller and narrower in a way. All right, I'd like to investigate some other values. So far, all of the values that I picked were numbers that were bigger than 1, right? The original coefficient would have been 1x squared. So far, everything I've multiplied by was bigger than 1. Let's take a look at what happens if my multipliers are smaller than 1, fractional multipliers or decimals. Turn those off. And this time I'm going to do y equals 1/2 x squared. Did you notice this time it appeared to get wider? We call this a vertical shrink. Again, notice right here at 2, the original function was 4 for the y value. Now it's literally half of that, or 2. The y value has shrunk in half. I'll do one more. We could do 1/3 x squared. And notice that that one's even a bit wider still. The smaller the fraction, the more we shrink it vertically. So let's see if we can put that into some words. If a is bigger than 1, we get a vertical stretch. Essentially, our parabola gets narrower as that graph is stretched in the vertical direction. And assuming a is still bigger than 0, if a is less than 1, like my 1/2 and my 1/3, we're going to kind of shrink it in the vertical direction. It looks wider because all the y values have come down a bit. All right, next one. And actually, I'm going to take a look at the next two together on Desmos, and then we'll come back and put it into words here. But in both of these cases, notice that we're making a change to the x value inside the parentheses before we do the squaring, right? So I'd like to investigate what happens if I add a number, and also what happens if I subtract a number from x inside those parentheses. So there's my parent function, y equals x squared again. And let's see, the first one on my list was x plus h. So let's do x plus 2 squared. If you look at that graph, how is it related to the original red parent function? Look specifically at the vertex. Does it look like it's just been kind of pushed over by 2 units? The shape looks exactly the same, right? I haven't changed the shape of the parabola or even the size of it, really. All I've done is push it to the left so that the new vertex is -2, 0. Let's see if we keep that up. We'll do one more. Let's do x plus 5 squared. Green graph here. And notice my vertex is now -5, 0. So indeed, we seem to be continuing to just push our graph to the left, by however many units I have in that h value. Let's get that much down. So the graph shifts left by h units. If I have my original parabola here, the new parabola was over here, moved left by however many units. All right, probably you're predicting already what's going to happen here, but let's just verify it. What if I change both of these pluses to minuses? Indeed, our graph is now moving to the right. Right there's my original parent function in red. The blue one, the x minus 2 squared, has been moved to the right 2 units. And the x minus 5 squared has been moved to the right 5 units. So the x minus h squared, the graph shifts right. By h units. And again, if the original looked like this, then our new graph has moved over to the right. Notice in both of these cases, our graph moved horizontally. When I make the change to the x, that is before we square, these are going to be horizontal shifts. In our last two in my chart here, notice this time I'm squaring the x first and then adding a number or perhaps subtracting a number. So let's look at those last two. Back to my original parent function, y equals x squared. And this time I'm going to do y equals x squared. And then let's add 3. And you'll notice the graph has shifted up. I'm going to move this down so we can see a little bit better. Same shape, same parabola. It's just moved up 3 units. If I did x squared plus 5, once again, the graph has just moved up 5 units. Notice how the vertex, those y values, are just moving up by whatever k value it is that I've added there. And I think we can get this all in one graph. Let's do the minuses as well. What if I did x squared minus 4? You'll notice that new green graph has moved down 4 units. So if I add, I move up, and if I subtract, I move down. X squared plus a number, graph shifts up by k units. That was my original. My new graph is just moved up. And if I have x squared minus k, the graph shifts down. By k units. So again, if that was my original parabola, the new one has shifted down. All right, this chart is the first of many times we're going to see something similar to this in this course. This whole idea of starting with a parent function and then noticing how in predictable ways changes to the algebraic formula make very predictable changes to the graph is something we're going to see over and over again this semester for different parent functions as we move forward in the course. So this is something I really want you to get to know and get used to. Just so that you know, by the midterm, you will have to know how to do the shifting without making reference to like a page of notes or a chart like this. When you do this enough, it becomes kind of almost automatic, hopefully. You'll get really used to it. But just keep in mind, this is one of those things that you will need to get to know. Again, we'll do this 5-6 times in this class for different parent functions. And these same predictable changes are going to happen every single time. All right, so we are now going to graph some shifted or transformed parabolas. Again, by hand, what I'm going to want to do first is identify the vertex. We'll do that by using the shifts, right? How is the vertex moved, left or right, up or down? We'll need to find the zeros and x-intercepts. Remember, the x-intercepts are where y equals 0 or where the function equals 0. So we'll end up solving the equation y equals f of x equals 0. By the way, when you think about setting an equation of this form equal to 0, can you kind of see that probably the square root method is going to work out really well? We already got something squared, right? So look for the square root method when we're finding the zeros and x-intercepts. Next thing is the y-intercept. To get that, we'll just set x equals 0. And then a last little note. When we are graphing a parabola, I'd like you always to plot at least 2 points in addition to the vertex. Oftentimes, by the time you have the zeros and the y-intercept, you'll have those extra 2 points that you need. But once in a while, for certain ones, we just don't get that lucky and we've only got 1. When that happens, you're going to see that whole idea of symmetry and the axis of symmetry come into play to help me out there. So we'll talk more about that when we get to it in one of the examples. All right, you might want to keep your little chart out for now, unless you're already familiar with this. And let's take a look at this first one. All right, so I'd like to identify the transformations present in my function, and I'll use that to find the vertex first of all. So as I look at this, I'm going to notice that inside the parentheses, I've subtracted 4 from my x. Remember, inside the parentheses is a horizontal shift. And because this one is minus, it's to the right. Right? When it was minus, the graph went to the right. So I'm going to say first, right 4 units. Outside my parentheses, I have that minus 9. And outside the parentheses, oh, I never actually added to that. This is my vertical shifts, sorry. So outside the parenthesis are vertical shifts, and this is minus. So notice this one would be down 9 units. There's no multiplier here, so there's no vertical stretch or shrink. There's no negative, so I don't have a reflection. That's it, just right 4 units and down 9 units. So what I'm going to do is, hopefully your facing page should look like this. I'm going to say if I've gone right 4 units and down 9 units, that puts my new vertex right there at the point for negative 9. As long as I have the vertex, I actually can draw the axis of symmetry if I want to. Remember that the axis of symmetry always goes right through the vertex. If you look at the parent function, it's just a vertical line through the vertex. So, if I want to, I can draw my axis of symmetry right now. Oh, let me make this a little bit easier here. I usually draw it as a dotted line because it's not really part of the graph. It's more of a guideline. And that vertical line would have equation x equals 4. Every point on that line has x value 4. So that's my axis of symmetry. X equals 4. All right, we got to do a little bit more work before we come back over here and do any more. So, next thing I'm going to do is look for the zeros, which are very closely related to the x-intercepts, right? To do that, y, or f of x, is set equal to 0. And so if I go back up here to my equation and put 0 in for f of x, my equation now looks like that. As I mentioned, problems that are given to us in vertex form, when I get to this stage of solving that quadratic equation to find the zeros, usually the square root method is going to work really well. I've already got something squared. If I bring the 9 to the other side, so I'm adding it, it'll be positive. I'm now set up exactly the way I want to be for a square root method. So I'd have plus or minus the square root of 9 equals the square root of x minus 4 squared. It's plus or minus 3 equals x minus 4. So either x minus 4 is positive 3 or x minus 4 is negative 3. This is going to give me x equals 7, and this will give me x equals 1. Okay. Those are the zeros, the values of x that make the function equal 0. If I want to turn them into actual points or x-intercepts, I just had to include the fact that the y value is 0. So 7, 0, and 1, 0 are actually my x-intercepts. It's a very subtle difference, right, between when we talk about zeros and when we talk about x-intercepts. Zeros are just the x values that make the equation equal 0. X-intercepts are actually points on the graph. So let's go over to the graph and we'll add that information and put those on there. So 7, 0 is an x-intercept, and 1, 0 is an x-intercept. And I'll add that here. The zeros were x equals 1 and x equals 7. X-intercepts 1, 0, and 7, 0. Okay. By the way, notice you should already be seeing the graph kind of take shape. Can you kind of imagine what that parabola would look like already? Okay. We're going to add one more point to our graph before we actually draw it, and that is the the y-intercept, rather. The directions to these problems are going to say show your work finding these zeros, x and y-intercepts by hand, so that's what I'm doing over here. The y-intercept just means that I'm going to put in x equals 0. Right? We've seen this before, but again, just a reminder, the x-intercept, y equals 0, the y-intercept, x equals 0. To find an intercept, you always set the opposite variable equal to 0. So f of x or y would be 0 minus 4 squared minus 9. Negative 4 squared would be 16 minus 9, which is 7. And my y-intercept is 0, 7. So I'm going to add that to my graph. 0, 7 right there. And I can add it to my list as well. My y-intercept is 0, 7. Now at this stage of the game, you really can just sketch, but I would like to point one thing out to you. We actually, kind of for free, get an extra point that we could use to help guide us because of symmetry. Right? From the axis of symmetry, notice how the x-intercepts, one was 3 to the right, one was 3 to the left. Look at the y-intercept. it's 1, 2, 3, 4 units to the left of the axis of symmetry, which means there had to be another point, 1, 2, 3, 4 units to the right. So kind of algebra free, we get that extra point, which can help us just to kind of guide us as we draw our parabola. All right, we know what a parabola looks like. So use those points as guidelines and sketch it in. All right, we have a few more questions to answer. Our domain here. This graph goes up forever and also slightly to the left, so it keeps going left forever. And again, on this side, it goes up forever, and it'll keep going to the right forever. So as far as the domain, negative infinity to the right would be positive infinity. My domain is really all real numbers, from negative infinity to infinity. That, by the way, really won't change for any parabola. We'll always have a domain that goes from negative infinity to positive infinity. The range is a little bit more interesting, however. Although we do continue to go up to positive infinity, we don't go down forever, right? In fact, the smallest y value on this graph is right here at -9. So remember, we always read our intervals from smallest to largest. I'm going to say my range goes from -9 and then keeps going up to positive infinity. By the way, did you notice that I used a bracket on that -9? -9 was our vertex, right? The graph actually does contain that point. It hits that -9. So I need to include it with the square bracket. All right, finally, intervals of increase and decrease. I'm going to try not to mark up my actual parabola too much. This graph is going to start decreasing, right? As we read from left to right, we're going downhill until we get to the vertex. So as far as the x values are concerned, all of these x values correspond to places that are decreasing on the parabola. So from negative infinity to 4. That was that decrease. We always use parentheses for increase and decrease, never brackets. On the other side, starting here at the vertex, which corresponds to x equals 4, now the graph is going uphill or increasing, and it will continue to do that forever. So we're increasing from 4 to positive infinity. Okay. That x value of the vertex is always going to be where it gets broken up and changes between the increasing parts and the decreasing parts. All right, I've got one more graph that's given in vertex form for us to play around with. This one I've got f of x is -1/2 times x plus 4 squared. So thinking about the transformations, I have a negative out front here, and then I also have a multiplier of 1/2. And I'm kind of going to talk about those separately because they each tell me about something, right? The negative sign is going to turn that parabola upside down, or formally we say it reflects across the x-axis. And then the multiplier of 1/2. Since that multiplier is smaller than 1, this is going to be a shrink in the vertical direction, or I might just say it's a vertical shrink. Visually, it's going to make it look wider, but that's only because my y values have been shrunk, so it doesn't go up as fast. All right, we got one more thing going on here. Inside the parentheses, I've got that plus 4. added to the x. Inside the parentheses is a horizontal shift. And the plus 4 would actually make this go left 4. Again, you can always refer back to your chart for now until you kind of get used to it. Okay, so thinking about my graph, and I'm just going to locate my vertex right now. The only thing that really moves the vertex is this left 4. So when I think about what the graph's going to look like, the vertex is going to go 4 to the left and be at negative 4, 0. If I want to, I could go ahead and draw in the axis of symmetry right now as well. It's always the vertical line through the vertex. And the equation of that vertical axis of symmetry would be x equals negative 4. All right, that's what I got so far. Let's go back to the page where we can do some work here. And the next thing that I'd like to find are the zeros, which also give me the x-intercepts. X-intercepts, which means y, or in other words, f of x, is equal to 0. So I'm going to say 0 equals negative 1/2 times x plus 4 squared. I can divide both sides by negative 1/2 to get rid of that multiplier. And 0 divided by pretty much any number other than 0 is still 0. On this side, I can divide out the negative 1/2, and I just have x plus 4 squared. I can use the square root method. Square root on both sides. And this one's kind of interesting because square root of 0 is 0, and it doesn't really matter if that's positive or negative, right? 0 is 0. So I just get 0 equals x plus 4, meaning this time I just get one solution to that equation, meaning I only have one 0, or in other words, just one x-intercept. So x equals negative 4 is the only 0. If I want to write that as an x-intercept, I would write it as the point, negative 4 is 0. Right? Now I wanted you to see where that comes from algebraically, but notice we kind of already knew that. Because we only shifted our vertex to the left, the vertex actually is the x-intercept. The vertex lies right on the x-axis. We really already had that, but now we've also shown it algebraically. So my 0 is x equals negative 4, and the x-intercept is negative 4, 0. All right, one more thing I can get. So far I don't have much information, right? All that work and all I've got so far is 1 point on the graph. But we certainly can get a y-intercept, so let's do that next. For the y-intercept, we put x equal to 0. So I'd have f of x, or y, equals negative 1/2 times 0 plus 4 squared. So that would be negative 1/2 times 4 squared is 16. So I get y equals negative 8. So my y-intercept is 0, negative 8. All right, I'm going to plot that in my graph. It's right there. And I'll go ahead and list it in the little chart here. 0, negative 8. Now this is one of those times where it's not just a convenience to use symmetry. I really need to use symmetry if I'm going to follow the directions where, remember how I originally said I want you to make sure that you have at least 2 points in addition to the vertex. This time, other than the vertex, I've only got 1 point. So I really want to use my axis of symmetry to my advantage this time. And it looks like I'm 1, 2, 3, 4 to the right. So if I put 1, 2, 3, 4 to the left, I know I have another point on that graph. Now I have at least 1 point plus the vertex, and it's okay just to draw. And this is going to be that reflected or upside down parabola. By the way, I don't expect perfection by any means, as long as you got the basic parabola shape, that's fine. The one thing that I'm going to be picky about is make sure your vertex is kind of a smooth, rounded, sort of a U shape, not a sharp V shape. The V shape actually is a totally different graph, so we'll learn about that actually in pre-calc next class, but make sure you get that rounded vertex. All right, our domain is still negative infinity to infinity. Notice it's going left forever and right forever. As far as the range, this one goes down forever, so down to negative infinity. But the largest y value right here at the vertex is 0. So my range goes from negative infinity to a maximum value of 0. My interval of increase, again, we always read left to right, and this graph is increasing right away. So all through here, we have an interval of increase from negative infinity to negative 4. We then have an interval of decrease, going to decrease forever, starting at negative 4. And for all other x values after that, this is just going to keep going down further and further. So from negative 4 to infinity is our interval of decrease. All right, so that's our 2 examples for if our function happens to be given in vertex 4. All right, next we're going to look at a couple of examples where the function is given in standard form, or sometimes we call it expanded form, right? It's written out in that ax squared plus bx plus c form. Unlike the vertex form, we won't be able to predict any transformations. We can't tell if this parabola is going to move left or right or up or down or whatever. So in this case, we're going to have to use a special vertex formula to locate our vertex. This is what it looks like. The vertex is located at, for x, I plug in values to the formula minus b over 2a. Notice it's like the little piece of the quadratic formula without the radical, right? That's no accident, actually. To get the y value of the vertex, I'm going to get the y value just like I can get the y value given any x value, right? Once I know the x, I can just plug it back in the function, right? And that'll give me the y. So mathematically, it looks like this. F of minus b over 2a. But basically, we're just going to plug in our x value into our function. All right. When we have equations in this form and we are eventually going to want to find the zeros, in other words, set them equal to 0, we'll have a standard form equation, not particularly conducive usually to the square root method. So this type of problem, you're probably going to be looking more at either factoring or a quadratic formula. to find the zeros. And again, we'll see that in our examples. All right, let's try this first example. I have my function here, and in order to find the vertex, I am going to use my vertex formula. X is minus b, so b is actually -4. It's minus a -4, or you can just write +4 right away. Divided by 2a, and notice a is -1. So I actually have 4 divided by -2, or an x value of -2. To get the y value for the vertex, I just take that -2 that I've already found and plug it back in my function, which is always going to give me y. So let's see, a lot of negatives here. I got a negative, and then I have -2 squared. Subtract 4 times -2 plus 5. Again, based on your own comfort level, you can either do this in your head or you can do it using a calculator or Desmos. I have 5 plus 8 is 13. 13 minus 4 would be 9. So my vertex is -2, 9. Let's put that on our graph. There it is. And I'm going to go ahead and just put in a little dotted line for my axis of symmetry. We've already seen those can be kind of helpful. So x equals -2 this time is my axis of symmetry. All right, next I'm going to look for the x-intercepts, also called the zeros, right, or very closely related to the zeros. And that's where y, or f of x, is equal to 0. So I'm going to have 0 equals -x squared minus 4x plus 5. I can try to either factor or use a quadratic formula in that form, but again, I have a really strong preference for a positive leading coefficient, especially if it's going to factor. I don't know yet, but it's a lot easier for me to factor when I'm thinking about a positive leading coefficient. So I'm just going to go ahead and move everything over to the other side of the equation. I'm going to add the x squared, add the 4x, subtract the 5. And that's now equal to 0 on the right. Or you can think about multiplying the whole equation by -1 if you prefer, right? It's the same result. All right. If this one factors, it's going to be a nice one because I just have 1x squared. So it has to be x times x. And I'm hoping I can find a sum of 4 and a product of -5. 1 and 5. If I make the 1 negative, then the product is negative, and that does indeed add up to +4. So x minus 1, x plus 5 are the factors. And that means that x minus 1 equals 0, or x plus 5 equals 0, giving me zeros at x equals -1, and x equals +1, and x equals -5. I could write those as the x-intercepts by making the points, putting the y equals 0 in, right? So 1, 0, and -5, 0 are my x-intercepts. Okay. Let's just go ahead and get the y-intercepts while I'm over on this page, and then we'll bring that all over to the next page at once. The y-intercept I have to put in x equals 0. So I would have y equals Negative 0 squared minus 4 times 0 plus 5. And of course, all that's just 0, so I just end up with y equals 5. And my y-intercept is 0, 5. Okay, I'm going to put the x and y-intercepts on my graph. So x-intercepts, 1 and negative 5. Positive 1, negative 5. Zeros, x equals 1, x equals negative 5. Technically, then the x-intercepts are 1, 0, and negative 5, 0. The y-intercept was positive 5. So plotted that on the graph up here at 0, 5. And I really do have enough to kind of sketch in my graph, although again, that symmetry is so handy, I'm going to use it. The y-intercept is 2 to the right of the axis of symmetry, so I'd have to have another point that's 2 to the left. Just gives me one more point to kind of aim for when I draw. And I've got this upside down or opening down parabola. Right. Before I go on and fill in the second column of the chart, I wanted to mention something. We had said that when we have an equation in standard form, we're not really able to just use the equation to predict the shifts. Notice that really there's nothing here that would have predicted that I was moving 2 to the left and up 9 to get to my vertex. There is, however, one thing that can be predicted from that standard form. Did you notice that our parabola was opening down, or upside down, if you will? Anytime I have a negative leading coefficient, that is one thing I can predict from the standard form. That negative leading coefficient is always going to give me the parabola that opens down. Or if you prefer, you can kind of think of it as upside down compared to the parent function. Okay. Other than that, I can't predict a whole lot from the standard form. I can't predict the vertex, the lefts, rights, ups, downs, but I can at least say if the negative leading coefficient is there, I know I'm going to have that upside down parabola. All right, let's finish out our little chart. We want domain and range, and again, as always, for parabolas, our domain will be negative infinity to infinity. As far as the range is concerned, this keeps on going down, so negative infinity, but the largest y value here is at 9. So my range will go from negative infinity to 9 with that square bracket. Include the 9. All right, this one is going to increase first, right? We're going uphill at first. And it increases until I get to my axis of symmetry. So from negative infinity to negative 2. And then after the vertex is hit, it decreases from there on. So from negative 2 to infinity, we see the downhill or the decreasing graph. Okay. Again, with intervals of increase and decrease, always use parentheses. You don't even have to think about it. All right, let's do one more standard form graph. I've got my function here, and notice that the leading coefficient is a positive 2. So the only thing I can really say from this standard form is I'm expecting this one to be kind of the right side up parabola. Doesn't have a negative leading coefficient. Let's go ahead then and find the vertex using our vertex formula. X equals minus b over 2a. So that would be minus 4 over 2 times 2. And negative 4 divided by 4 is going to give me an x value of negative 1 for my vertex. Once I have the x, I can always just plug it in here to get the y. So 2 times negative 1 squared plus 4 times negative 1 plus 5. Let's see, that's 2 plus 5 would be 7. 7 minus 4 is going to be 3. So my vertex is at negative 1, 3. There it is. And again, I like to just add in my axis of symmetry at this point. Always the vertical line through the vertex. So x equals negative 1. All right, I'm going to go back and get all of the intercepts, x and y, and then we'll plot those on our graph. The x-intercepts are zeros. We get them both the same way. This is where our function y, or f of x, is 0. So I put the 0 over here. Like so. All right, I like the form this is in because my leading coefficient is positive, so I'm going to work with it the way it is. And let's see, if this is going to factor, I would need a sum of 4 and a product of 10. Remember, this would be the extended sum and product method. Unfortunately, I don't think I can get that, right? 10 is 1 times 10. That's not going to do it. 10 is 2 times 5. Can't get a sum of 4 that way. So I don't think this one's going to factor, meaning I will have to use the quadratic formula. So x equals minus b, be negative 4, plus or minus the square root of 4 squared, minus 4 times a is 2, times c is 5, over 2a, 2 times 2. That's negative 4 plus or minus square root of, what have I got here, 16 minus 10 times 4 would be 40, negative 24 over 4. Now at this stage of the game, I actually already know something. Certainly that's going to become an imaginary number, right? So a complex number overall. And I'm sure you've noticed that we've never plotted an imaginary number on a graph, right? So if my results are going to be imaginary numbers, I will not have any x-intercepts. I can't plot an imaginary x-intercept on a graph. I still have zeros for my function. The zeros are going to be complex numbers. But because they're complex, that translates into no x-intercepts. So let's finish this to get the zeros. I would break that down. Square root of negative 1 is going to be the I part. And then if I break down that 24, I could go with 4 times 6. So this is going to give me 2i times the square root of 6. And anytime I've got the complex number with the real and the imaginary parts, I always write them separately. So I'd have negative 4 divided by 4 would be negative 1. Plus or minus 2/4, I could reduce that to 1/2 I times the square root of 6. Right? Those are the zeros of the function. Oops. -1 plus or minus 1/2 I square root 6. Sorry, I almost put my -1/2 in the wrong spot there. X-intercepts, because those are imaginary numbers, imaginary zeros, so there are no x-intercepts. I'm just going to say none. Right? So once again, at this stage of the game, I don't have any more information about my graph other than the fact that I've got the vertex there at -1, 3. I'm going to have to rely on my y-intercept to give me more information. So let's do that. For the y-intercept, we set x equal to 0. So y would be 2 times 0 squared plus 4 times 0 plus 5, which is just going to be 5. Y-intercept's really easy to find, right, for the standard form. And so we're just going to have 0, 5. There. And this time I really need that symmetry to help me out here. This is just 1 to the right of the axis of symmetry, so I'll also have a point 1 to the left. And that at least gives me the 2 points that I need in addition to the vertex. Notice this is going to be on the narrow side, so I don't have a whole lot to go on, but just make sure you go through the 3 points that we actually have. Domain remains -infinity to infinity. The range, smallest y value here is 3, and then it goes up to infinity from there. So from -3 to infinity. And then finally the intervals of increase and decrease. This graph starts out decreasing until we get to that axis of symmetry. So it decreases from -infinity to -1. And it increases on the other side of the vertex. From -1 to infinity, it's going uphill. All right, I want to just mention one other thing here. Could you have predicted that this graph would have no x-intercepts even before you did the quadratic formula? I would suggest we actually could have. As soon as we saw this positive leading coefficient, right, we knew that we had kind of that standard opening up parabola. Basic shape's going to look like that. And once we found out that our vertex was at -1, 3, knowing that the graph had to open upward, there's no way it was going to cross the x-axis, right? Now, algebraically, we still had to show that, and we wouldn't have been able to find the zeros without doing the quadratic formula. But already in our heads, we already really knew, hey, that's not going to hit the x-axis at all. It's impossible. All right, I'm going to go ahead and say that we probably should pause here. This has been a long video already, and we'll do our last form or two in the next one.